Let's get going. So we're recording. We're going to talk about queues today, which is another abstract data type, but we will also dig into the implementation of it. And then we'll have a little light introduction to a special kind of a queue. It's really quite different, but we still call it a queue. It's called a priority queue, and it's a super powerful data structure, abstract data type, actually. So this will set us up really for kind of moving into algorithms that utilize these things. So from now on, after this week, when we say, oh, it's a queue or it's a stack, or let's do that with a queue and a stack, we'll know what we're talking about. And some of our code base is going to eventually circle back and pull in these coding solutions that we're looking at today. So we are going to build everything from scratch, which I know it may be a little annoying because we have all these great libraries, but this will make sure we all understand the foundations of everything. After this class, we'll probably all go out and use libraries from here on out. But so important dates to remember. I hope I got them right. Last day to drop is this, with a W, is this Friday. Our midterm is, I had it wrong, but it's Thursday, October 16th. That's basically our lecture 16. So we're at lecture 8. So we got a ways to go before we get that. That'll be in the classroom. We'll have a full 3 hours of that for that. If you need it, full 3 hours, and just one try on that one. I think I mentioned that before. If you're not going to be here for any reason, please let me know well ahead of time so we can make plans for that. Generally, I try to not do that, but I realize life happens. So we did our stack array. Many of you are kind of still looking at that. I'll try to get those graded soon. We have an optional lab 8 today. This is kind of a strange little technique. You can implement a queue using 2 stacks, but it's probably not very efficient, but it's there as an optional lab if you want to just, use that stack class one more time, just getting familiar with using that in the main section of your program. And you can come back and do that at any time before the end of the semester. So any lab that says optional is there for you to come back to if you want to push your lab grade up a little bit by the end of the semester. Then we have our homework 2 coming up, which hopefully everybody's starting to think about, and our quiz 2, which will cover 5, 6, 7, and 8. So kind of a little bit of a busy weekend. For today, we want to just review very quickly the abstract data type idea to make sure we're all clear on what that is. And a real quick glance at the performance, and then we'll introduce the idea of a queue, something that you kind of like waiting in line to be served for something. So between stacks and queues, this covers a lot of the foundational territory of some of the most famous algorithms out there. So, we may not even look at the code again after this, but we'll always be talking about them. And we'll always want to be a little bit aware of what it costs to have a queue, because it's going to end up being baked into a lot of other recipes that we're going to use. So as we said last time, at the ending, a queue is really people kind of jumping in line. So the first person in line, in theory, should be the first person out. So that's the classic definition of a queue. We call that a FIFO. And we'll kind of have our queues moving from left to right, just in terms of our notation. That's just, me. If you go to Program IZ Pro, their representations of, go from the other way around, which can be confusing. So just heads up on that. The NQ side is when we push in, and the DQ side is when we pop out. Okay. So pay attention to where the push end is and the pop end is, and that'll clear things up for you. Okay. But you might want to think about it as being the person who's been in line longest is over by the DQ side, and the newest person is on the NQ side. So a lot of quiz questions throughout the course, and eventually, midterms and stuff, we'll use this notation. I try really hard to be consistent about it. So, hopefully that'll help avoid some confusions. Now we'll see 2 implementations today, and they really are pretty similar. Generally speaking, we don't need a double pointer implementation of our queue. We really only want to pop from the oldest and push in the newest, and maybe we want to print the queue in one direction. So it's really just about figuring out which direction we want to traverse the queue if we want to print it, or if we need to print it at all. So, but we'll look at a couple of implementations, and then we'll introduce this very cool thing called a priority queue, where people sort of bubble to the front of the line, like in a hospital emergency ward. It's like, okay, I got there last, but my arm is, half attached. I got to be pushed to the front of the queue. So priority queues are a very cool way of getting things to the front of the queue that need attention without sorting the whole queue, which is a really neat trick. So we'll look at how we do that here next week, I think. And it's kind of a queue, but it's a little different than the one we're going to introduce today. So quick concepts from last time. Remember that an abstract data type is really more of an idea, not so much code. And so if you can sort of express something sort of visually in a graphical form or a symbolic form, you're probably dealing with something like an abstract data type. Now you could say, oh, isn't an array an abstract data type? And people can debate that one all day long. Okay, yeah, I suppose you could treat it that way. But array is really an example more of a data structure. It's an implementation that's specific. So some things get a little murky, and I'm not really one for like testing you on the differences, but of course people will expect when you come out of this class, you'll kind of know what we mean by an ADT or an abstract data type. And so it's just kind of deciding how to represent the problem, okay? And deferring the implementation until later. So if we were to do it with arrays, we said, we got to deal with allocation, deallocation. Linked lists are a little bit more of a direct analogy for that stack idea. So probably a lot of stacks are implemented with arrays, unless we're on an architecture, with linked lists, unless we're on an architecture like maybe an Arduino or something with not enough memory, and then we might just deal with those in an array format, okay? So a little bit of singly linked list warm up for us we saw last time. And as with many things in this class, we're going to wrap it all in a kind of a class name that describes what we're doing with that and maybe hints at its implementation. So this is all just good C++ review syntax for those of us who are just getting back into it again. Okay. Now in this class, I will try to keep us all in one file. Now I know in more real world C++ development, we tend to separate the interfaces in .h files and the implementation in .cpp files, but I'd really like to simplify that for all of us. So in this class, I'm going to really try to keep everything all in one main.cpp file or kind of one class file so that we don't try to turn ourselves into an advanced C++ class. Now, just a little bit of the math, and then we will go on. But remember that in terms of the analysis, the number of times we're going to divide over the lifetime of an array of size n, if we started at 1 and we doubled it every time, is given to us by the log of n, right? So if the final size is n, log base 2, if we were doubling every time, tells us how many times we doubled. So we should be able to kind of start to figure that stuff out. And that just provides a really handy way to apply this geometric series function. We can replace the q with the log 2 based n, which the identity kind of tells us that's just going to be n, right? So we end up back with this 1 minus n over -1, and that's essentially going to be our kind of n minus 1 or linear behavior. So that's more about the analysis than the cleverness of the doubling idea, but hopefully it just gives you another way to appreciate that log base 2 kind of relationship. So for today, we're going to look at queues, which again are first in, first out, which is another way of saying FIFO a lot of times. So if somebody says, hey, what's a FIFO structure? You'll say that's first in, first out, and that's a queue. And we'll, again, in queue from the left side, and you can think of it as, filling up, or growing toward the left, and then we'll dequeue on the right side. So there's no prioritization in this particular implementation of the queue. We just kind of, the oldest gets dequeued first, okay? So when we dequeue from that side, okay? So we haven't thought about how we would build this, but it's fun to think about how we would build it. It's like, oh, I could think of at least 2 ways to do that, okay? So the API, or the abstract data type maybe is a better way, is just enqueue, dequeue, and probably a constructor, and maybe size, right? And is it empty? So just some very basic things, okay? So get size should return that. And, my happy faces mean, they're expecting to get served very soon, and everybody at the end of the line, not going to get served for a while yet. Okay. So there's our first in, first out. Okay. So implementation, we're going to look very briefly at what if we were going to do it with arrays, but we're not going to really do it with arrays in this class. But let's just quickly sketch it out, and then we're going to move on to linked lists, which we're going to do a lot of over the next couple of weeks because we really want to strengthen our linked list skills. So we'll look at doing that, and the performance for linked list is essentially constant time. Right? So we'll find that it's really, really quick, regardless of the length of the queue. We're using a linked list to actually put stuff in and take it out. So that's a really good thing. Arrays we'll see is a little bit different because, of course, if we run out of space, we have to double the array, right? And we just sort of saw that analysis for our stack, kind of the same thing if we were going to implement this with a queue. But let's look at how we would do an array queue implementation. So if I kind of have some letters in here and I align the oldest to the far right side, you can kind of see what's going to happen. Eventually, we're going to run out of space, but we might be, NQing and DQing in some arbitrary order. So if we're DQing, we just got to remember to move the head counter over. We can't really erase a single element of that array, and there's really no reason to reallocate it just yet. So we just sort of move our pointers around, and I'm talking about integer pointers here, like, position 8 and position 1 is our head and our tail, right? And eventually we might need to rebase or realign everything. If it, gets really low, we might slide stuff over to the right, or we might, shrink the array or double it, kind of like we saw with a stack. So we're going to have that same kind of behavior, which is that, over the lifetime of this thing, it's going to probably grow and shrink and cost us a little bit. And that might be a cost you're willing to pay. But, we don't have to deal with any pointers. We're just storing whatever that data type is in there. Okay. And I guess I'll say that it's good to remember that although this is a character array, this could be an array of type node, where each position in the array holds an entire instance of a class. So any data type that we can create in the form of a class could be copied over one of those array positions entirely. So we don't have to just point to an instance from position 1, for example. We could actually store the whole instance in there, just like we can store an integer or just like we can store a character. So we'll come back and see some more examples of that. But, arrays can do quite a bit, right? We can store just about any data type we can imagine in there and get away with that kind of an approach. Okay. But we're not going to go too deep into that because we've already seen that, and it might make a good test question, but I honestly don't think I have done that. So, but it's a good one to think about. The linked list one is more interesting and probably more common. So here's our classic queued linked list implementation. So notice our blue arrows are pointing to the left. They're going to the what I would call next older direction toward the tail. So everything to the left of the A is kind of been next newer. Backwards. Next newer is on the left. So when we NQ, we kind of hook up one of those blue pointers, but we also keep track of the head and the tail there. Okay. And notice the newest one has a terminated or null pointing next newer, right? There's nothing newer than E. So we got to make sure the thing on the end there doesn't accidentally ever have a non-null pointer there, because we don't want to follow that thing. Okay. So that's what we want to do. And all we got to do is keep that thing in good health, and it's going to serve us very, very, very well. Okay. So the bluer one, we'll see, it will kind of keep that color consistent. But if we're going to print this thing, we're going to print sort of from the newest toward the oldest, because that's really the only kind of way we can do that. Okay. So even though our notation, unfortunately, is like the oldest is on the right side, when we print it out on the screen, we're going to traverse from the right. And so the A is going to end up going first, and then the B and the C and the D. So it's a little confusing maybe when we run our code samples. So I kind of regret doing it this way, but hopefully we can kind of power through it. Okay. So we're going to look at the code to do this. And it's a really great warm up because there are some landmines here that can blow up our code if we're not careful. Okay, so we'll look at what that code looks like. Okay. So hopefully everybody can relate to what a queue means. And remember that in C++, if I have a pointer that points to a node here, let's call this a node, and I have a head pointer, then that's a star, node star type of data variable. So head points to A, head next, therefore, would point to B. So if I'm saying head arrow next newer, I'm referring specifically to the B in that case. Okay. So in other languages, we might say head dot next newer, but here we're going to say head arrow next newer because head is a pointer. Okay. So C++ is a little different maybe in its notation than Python or Java or maybe even JavaScript. I can't exactly remember the syntax there, but we'll go through that with you. So we could extend that and just say, well, then head, next, sorry, that's a little typo, head next newer, next newer, next newer, and that would get us, down the train there, right? So that should be next newer there. So, but nobody wants to work that way, right? So what we want is, of course, a loop of some kind that's going to keep moving us down the train here. And I think many of us have probably experienced that in one form or another. But let's take a look symbolically at least how we're going to do that. So if we have something with nothing in it, of course, we want to point the head at the new node that we create. Make sure that the next newer node is sort of created null, or at least set to null, and then point the tail at that thing as well. So we got a couple jobs there, at least two things we got to do. If I put in another thing, I've got to hook the next newer pointer of A up to the new thing. I don't have to change the head in that case, but of course I have to update the tail, okay? And on we go. So we're really just sort of pushing in at the tail every time we end Q, and we just got to be careful that, there's a special case here, right? So this is the special case. In that case, I got to deal with head and tail, right? In this case, I really just got to hook up the old tail to the new thing and then update the tail. And we'll take a look at that step by step in the next couple of slides, okay? So if we DQ, we're going to just advance the head, and in theory, we clean up memory so we don't have a memory leak there. But the key thing is moving the head forward. Okay? All right, so let's take a look at our node class again. So we're going to have a simple string node. Now, I know we could templatize these nodes for folks who know what that means, or use generics if you know what that means in Java. But we're going to keep it simple. So our nodes for now are going to be, string nodes. But we could make it more general if we wanted to get a little fancy. But we're not trying to, be too fancy in C++ now. But here is our next newer pointer and our constructor. Okay, and so, again, for safety reasons or just to amplify it for everybody, I set it to null in the data member creation, and in the constructor, I do it again sometimes too. If you know the rules, you could probably skip this one or skip this one, but I tend to put them both in there because sooner or later somebody forgets them and becomes a problem. But there's my node, and so if I want to create a new node in C++, we say node star my node pointer equals new node. New always gives us a pointer. Always, always, always. Therefore, we have to have a star for the corresponding data type. New node gives a pointer to a node. Okay, so that's annoying, but that's our syntax when we do a dynamic allocation of a blob of data that represents a node. Okay, so now we're kind of holding on to this, ornament by a string or a pointer, the node pointer. And the next newer, of course, needs to be that exact same kind of pointer because we want to hook things up. So inside of our class, that is going to match the data type of this pointer out here on the outside. Okay, sorry for all this stuff floating around there. So my node pointer, has a value in the next newer. And if I make a new thing, if I create a new thing, I'm going to hook it up that way. Okay. So I think probably you guys have seen this in my other courses and in your travels, but I just wanted to make sure we're all clear how these things hook together. So this is kind of throwaway data here. It's just the next connector. This is the value we're really interested in, keeping going. Okay, the word or the data or whatever we're putting in there. Okay, and null PTR, NULL PTR is the modern way of nullifying a pointer. We don't set it to 0, and we don't use the word null anymore. We just use that NULL PTR. Okay. Let's take a look at where we go with this, right? So if I wanted to print the value associated with this thing's so annoying. I would say my node pointer arrow value. So my node pointer arrow reaches in the box. That's the analogy I like to say. My node pointer arrow, we're inside of the box. What do we want from the box? We want the value, okay? So that's kind of one way to think about this C++ syntax. The arrow gets us in the box. Then we say, what do we want from that box? So that's what's going on with node pointer arrow value, okay? So here's our class. We've got in the class, the instance of the queue itself has a head pointer. It's going to be private and hidden to the outside world. Nobody needs to know about that head pointer. They're going to operate on the methods of the class. And we'll have a tail pointer. We'll keep track of the current size, and off we go. So our constructor just needs to make sure that thing is null on both sides, and then we can get on with life by allowing the methods to control everything. So let's look at our NQ for starters, classic pointer stuff. So if we have multiple nodes in our queue, let's just start with that simpler case once, for example, number 1. So if I want to push something in at the tail, right, it's going to kind of go over there. That's our NQ. So I have a handle on the last one because I have that special tail pointer. So I'm going to increment the size, hang on to that thing, right, with a new temp pointer. And then I'm going to create a brand new node and move the tail pointer over to that brand new node. Okay, so that's our new, gives me a pointer to a node. And S is the string I want to put in there, right? And now I've got a new tail, but I got to hook it up. So I got to hook temp up to the tail. Now, what if there was nothing in the queue? This could crash our program if the queue was empty. So this is a really important piece of code. If we leave that out, like it will guarantee blow up at some point. So if temp was not null because of this initialization, then let's go ahead and connect its next pointer up to the new node. Without that if the thing was empty, there was nothing in there in the first case, you're going to crash because temp would have been null, and null arrow next newer is going to crash your program pretty quickly. Okay, so that if is crucial for keeping ourselves out of trouble. Similarly, if the head was null, right, originally, then we know we need to also update the head. So without that if, we would also have a pretty nasty crash on our hands, or we would have an unupdated head and sooner or later it'd come back to bite us. So there's lots of ways to write this simple little method, but there's a lot of ways to create bugs too. So if you see yourself writing twice as much code as that, you're probably okay. It's not wrong, but it gives you a lot more opportunities for making mistakes. So this is one way, probably one of the more optimal ways to write that without a whole lot of extra code. And it handles pretty much all of the bad cases, okay? So really critical stuff right there. Any questions on syntax so far, what these notations are telling us? Okay, so let's just go through 2 more examples here. So here is one node in the queue. So let's look at how our code executes, right? Same code, really, same code. So increase the size, point to the tail, which also happens to be the head in this particular case, okay? Create a brand new node, right? Move the temp over if it's not null. If it's not null, sorry, then we connect it up rather, right? Connect up what was there to the new tail, okay? And if the head is not null, then we're going to set it equal to the tail in this case. Or if it was null, we'll set it equal to the tail. So this will not be executed in this particular situation, right? Because the head is not null, right? If it was equal to null, we'll move that over, but it's not null, so we're not going to do anything with that. Okay? Same code as the previous slide, we're just executing it a little differently here. Okay. Okay. So that's our one node in the queue. Let's take a look at the last one, which is an empty queue. So here, create the new thing, right? We're gonna hook up. If there was anything there, we'll hook it up. But since temp is equal to null, then we're not gonna try to hook that thing up. We'll skip that. But the head is null, so we're gonna actually aim that at the new node on the end, okay? Same code, just kind of a different execution path through there. Okay? So that's our enqueue. Not a lot of code, but carefully constructed. And once done, right, it's pretty sweet because it's kind of bulletproof, right? Let's take a look at the dequeue. Again, we'll start with kind of a queue that has stuff in it. I want to get stuff off of the tail, off of the head, right? Decrement the size. First off, yeah, you got this one we often forget. If it's empty, then just print a message and return maybe, but get out of there. Don't try to do anything. Okay. Otherwise, we decrement the size. If the head is equivalent to the tail, that means that we're deleting the last thing and we have a special case. So we're going to set the tail to be empty. Okay. And then we're going to grab the head because that's what we're going to delete, right? And then we're going to steal its string. Okay. So we want to kind of take the string out of the head node. And then we will advance the head to the next thing, which in this case is null. So that little piece of code is also pretty clever because it turns the head to null if it needs to be, or it moves it to the next node, which in this case is that one right there, okay? And now finally, we can delete our temp, right? My animation's a little out of sync, and then return the string there, okay? And temp will just go away because temp is a local variable here, right? So temp's just holding on to an address, and so it's just going to disappear when we're done with our function down here. Okay? Not too much code, but important in its order. Okay. And the important thing to realize is, and this we sometimes do, and we'll do it in this class, is if you do this, you're like, I don't need that string variable. I'll just return temp value. But you already deleted temp, right? So that means you're following a pointer into an area of memory that's been deallocated. Yeah, C++ will let you do that. And sometimes it will crash and sometimes it won't. Nasty bug, really nasty bug. So, you want to just be super careful with your logic when you design these things. So we don't want to reach into memory after we've deleted it, and we can't really return anything, before we've deleted it. So, if we want to clean up memory, we got to copy it into a temporary string, delete the node, return the string, and then everything's clean again. Okay? Now you could say, well, what if I just don't delete this, right? And in this class, I'm not gonna, give you a hard time for that. But if you did that 100,000 times, you'd run out of memory, probably crash your program, okay? Or have a really huge memory leak. So proper code, we got to delete that thing before we return from our function, okay? Or come up with some other clever strategy to do that. So that's our DQ for example 1, okay? So let's take a look at, yeah, and this is a nasty bug, right? If you forget that one right there, that's going to cause some problems because you'll nullify your tail and you'll never be able to NQ properly anymore, okay? So sample 2, let's just take a look at 2 more special cases. I got just one thing, right? I decrease the size. If the head and the tail are equivalent, then nullify the tail, right? And then grab onto the head with a temp so we can steal its value. Okay. Get the temp string. head equals head next, but next is nothing, right? So that nullifies the head, which works very nicely. And then we can delete the head, okay? And return our string. And we're out. Okay? Again, not too much code, but handles all of the tricky cases. So last one, trying to do that. Of course, we're just going to trigger that return empty, and everything else is kind of ignored in that case. Okay. So again, you could write this a lot of different ways, and it's fun to actually write it, but you have to really be in a quiet room sometimes to make sure you haven't left any of these cases unhandled, because they sneak up on you, and it doesn't crash right away, as many of you probably know. So let's do something that's should be pretty doable for all of us. We want to print. So from oldest to newest, so we'll write this code here in just a second together. But we want to start at the head and print. And we only really have pointers in one direction, so that's going to be it. It's going to be from oldest to newest, okay? So it's going to be a little reversed on the screen from the way I'm showing it in class here. So essentially, we got to print what's at temp and then say temp equals temp next newer, okay? So until it's null. So temp's going to keep going until it falls off the train, and we know we're done, okay? That'll be our easiest way to actually do that. So let's take a look at the actual code for this, and I will tour you through it, but then I might let you finish it here. Get this out of the way and try really hard not to ruin my share here, okay? And we'll save everybody's eyes, make it a little bit bigger. Like so. All right, so here's our node up top, nice and simple. Next newer, constructor, okay? Our Q class. Remember, these are available to us as long as we're inside of the Q class scope, okay? So I can just refer to them as head, although some people like to call it this arrow head. If anybody is familiar with this from other programming languages, we're just going to call it head and tail when we're inside. So here is our constructor, right? Just making sure everything is, null, little message to tell us that what's going on. Here's our NQ code. This stuff's already written for us. Our DQ code is written for us, so we don't have to worry about that. We just saw that code. Empty is just asking whether the size is 0 or returning the size. And so we want to print this thing, okay? So we're going to print something of the current size. So the one mistake we do not want to make is we do not want to change the head. So we really want to say something like node star temp equals head, okay? And then I want to say while, okay, let me let you think on that for a moment. While something is true, right, we want to say cout temp arrow value, and we'll just put an ENDL on that, okay? So how long do we want to go? Well, if temp is null, we're going to crash, right? So we do not want to access that value if temp is null. So the real trick is here, we want to go while temp is not equal to null pointer, okay? TR, like so, okay? And that's it, right? Once we go past that, we're pretty much done, right? And actually, so what I'll do is put a comment in there. Okay? So let's see if I can actually run that and not get into trouble. So, wow. Okay. So classic mistake. Beginning of the semester. What didn't I do? I didn't move temp forward. Temp equals temp next. It's almost like I did that on purpose. Next newer. Okay. I think I did that in the last class too. Okay. Is that how it's spelled? Let's see. There we go. Okay. So wow. Okay. There's the wow. So that's the head, right? Or where we DQ from over there, right? And I'll just do it. I'll say 2, 3, 4. Okay. So if I DQ, and I've written this code already, if I type an X, and this all is in main for, just to exercise our data structure. But if I say X, it should DQ from the head. So we shouldn't have a wow anymore, which is true, right? So we got rid of our wow. We X again to DQ. We get rid of our 2 and so on, right? And so none of these things should crash, even when it's empty, right? It says it's empty, right? So we don't have to worry about crashing anything. So again, that's just a great way to get to know a data structure, is to figure out how to print that thing out, okay? So hopefully nothing too earth shattering there for you. Gives you a good introduction to pointers and access it, okay? And we won't always search for null. We might need to do some other things. You'll see that coming up next week when we get into some fancier stuff with our pointers, okay? But for now, our while loop is going to go while temp is not equal to null. And remember, if you used head here, right, and you'll see this in some quiz questions, if you put head here and you advance the head, you're going to destroy the queue. We'll never be able to get back to the beginning of the queue again because you changed the official head of the queue. So we got to, in this case, make sure we get a temporary pointer to that so we don't ruin anything, okay? If you wanted to print it in the reverse order, or let's say you had some other reason to be able to access this in the reverse order, we need another set of pointers. We're going to double the cost of our pointers, and every pointer costs you 64 bits on a 64-bit architecture, so that's going to be twice that. So that's a little bit of an expensive thing for just printing. But let's say we wanted to do that, right? How would we modify this data structure to make it be able to go in both directions? It's less than you think if you do it carefully. So here's temp, right? So we want to kind of go, we know we can go that way, but we want to be able to go the other direction. Now remember, temp is a node star, okay? That's important, okay? Everything's got to match up, so that's our pointer address type, and it's pointing to a node, obviously, okay? An instance of a node, okay? So this idea in C++ is if you're pointing to something is of course going to be a star right next to the data type for the pointing, okay? So I think I made this point. If you move the head, you're going to destroy and never be able to get back. So you want to avoid that, okay? All right, double pointers. How do we do that? So let's say we add a next older pointer. You could call this whatever you want. You could call it previous if you want, and things might be a little easier to type, but that's what we want to do. And it creates a little bit of complexity for enqueuing and dequeuing, but not too much if we've done a good job designing our enqueue dequeue code already, okay? So if those pointers are there, we can just start at the tail and, do the opposite thing, just go until null, okay? But you can imagine what would happen if we forgot to nullify a pointer over here when we dequeue from the head. So it's really important to take care of management of those yellow pointers now, okay? So let's look and see how this stuff works out, okay? So we'll create the node. We will enqueue the node, right? We're enqueuing the node. So we're going to point the next newer to the current tail, right? So temp next newer gets the current tail. Okay, that's the first thing we got to do. Now we got to hook up the back pointer from the tail. Unfortunately, we haven't changed the tail yet. So we can just say tail next newer equals temp, okay? Or next older. Next older? Point the next older to the new node. Right. Have I got that right? I think I have that backwards. The older and the newer. These are the older, these are the newer. So I may have switched my notation here. Apologies for that. But you kind of get the idea. We're going to hook up both of those things before we update the tail. And the last thing we'll do is we'll update the tail. Okay, so the tail and the temp helps us kind of construct that before we do the final update. If you did it in a different order, you'd have a lot more trouble kind of putting this piece together. Okay, so now the dequeue on the other side, we grab onto the thing, we're going to delete essentially. We move the head in the next newer direction. Again, sorry for I think I got my notation wrong here. So the newer stuff is here. And then we delete the old head, okay? And crucially, we have to nullify that yellow one because otherwise somebody's going to just follow that thing right off the end and blow up your program. And we'll definitely be seeing that here in the next 2 weeks. We'll have a priority queue assignment where probably we'll have folks crashing because of that. Okay. So I'll remind you when we get a little closer to that. But we got to make sure we clean that up. So let's see if we can add the next older pointer. Again, I really apologize for the confusion about this. Next older is going to the right, and we'll see if we can add that. Okay. So the print queue has been written, and it will work on the next older pointer. We want to add the next older pointer to the NQ function to make sure that the next older pointer points to the old tail. So let me give you some code to work from so you guys can jump into this. Okay. So we want to make sure next older pointer of the new node points to the old tail. So tail next older equals temp. Okay. And then head next older equals null pointer, okay, on the DQ. Let me show you the code here for that. So your existing stuff is going to have one little change here, right? So next older, tail next older equals temp, okay? And temp is going to be equal to what was the tail, okay? Right there. That's really all we got to do to add to this existing piece of code. So let's just review again one more time. So we have this situation, and I want to make sure that when I add this new node to tail here, that I hook up it to the temp of that was the old tail there. So I'm just saying tail next older equals temp. And now we've kind of fixed that thing up there. Okay. That's all we have to do to that existing code for it to actually run for us, okay? Tail next older equals 10. I know it takes a little bit to take it in. You can see I even get kind of confused on this notation sometimes, okay? And then this one over here, the only thing we need to do when we delete is make sure we nullify the head's next older pointer. So that's that one over there, right? So the next older pointer over here is what we got to get rid of. Head next older, because that's what we're going to actually delete. Okay. Sorry. This is what we deleted. This is what's left. We're deleting this over here. So after we move the head equals head next, sorry, my animation is kind of not fully updated. We are going to delete what the head's next older pointer is. Okay. So there's nothing over here. So I think I have an example of this. Yeah, here's the DQ. Yeah, okay. So we come over here. If the head is equal to the tail, which it's not, right? But otherwise, we grab onto the head. We steal the string from that node. We say head equals head next, okay? And then delete the head, okay? So my head moved over, head equals head next. We delete the head, okay? And then we nullify that straggling pointer right there, okay? And then we can finally return that string. Okay, so a lot to take in there. There's kind of, there's only kind of best way to understand it is probably to try to write it, right? And you can write it from scratch, but we're not going to really make you do that per se. You will probably deal with this in about 2 weeks. So kind of put a mark on this slide to come back to it because this is some really helpful code right here. But you're more than welcome to kind of write this stuff from scratch when the time comes. But I know it's a little tricky, so I kind of put it up here for you to come back to in the future. Before we move off of this, though, any questions about the approach on this or the notation?
It's just turning it into a doubly linked list pretty much.
Yes, exactly. And so this is good code for, all sorts of stuff. When you add and delete things to a doubly linked list, there's a lot of really tricky maintenance like this, and we'll kind of be doing that. You guys will have a choice. Some of you will do stuff with singly linked lists, and some of you will choose to go the double path. I think there's a little bonus involved if you go down the double path here in about 2 weeks. So I'll remind you that when we get there. But this is, one way to do it. There's more ways to organize it. Okay. So that's our double linked list. And in this particular case, it's just sort of giving us the opportunity to move in both directions. So let's look at the implications of that. They're pretty obvious. If we did it with the array, we said we'd have that doubling cost. The isEmpty is constant time, no matter how big the array is. If it's representing a queue, we can always kind of know how big it is, or if it's empty. So those things are pretty obvious. Printing newest to oldest in an array is linear time, right? There's n things, so regardless of the direction, we're going to get n things either way, right? And it takes less space per data item than the linked list, because the linked list on the right side now is going to take, 2 pointers per node. Pushing is constant time, which is really nice. So we don't pay a cost over the lifetime of the array like we do if we use an array implementation. We just sort of put it in at the NQ side, and the pop is constant always, which is really great. So all things are kind of maybe a little better on the linked list side if memory is cheap, right? We just pay the cost for some extra pointers, and now we have a lot of flexibility, okay? So we just got to have a little extra memory there if we need to go in both directions, which is not always the case, but it's something that is useful for a lot of data structure things that we might do with linked lists. So nothing really, no big rocket science or math there. But the tricky part is in the debugging of that. Once you get it up and running, it works quite well. Okay. So we'll see uses coming up in the next 2 weeks for doubly linked lists. It's pretty standard stuff, obviously, for most data structure classes. It is a data structure, right? So the linked list is the data structure. The concept of the queue is the abstract data type. So the double linked list or the linked list or the array is how we implement the abstract data type. But the abstract data type is generally thought to be a separate thing from the choice of your underlying implementation. Okay. So let me introduce you to priority queues briefly. We're not going to do the coding. We'll get you out of here a little early tonight. And the lab is optional, or we'll get you into lab a little early. But this is a really cool data structure, and we will spend some time on it next week. But the idea is one I just wanted to leave you with, and it's that hospital line idea. So if we push or add or NQ into a priority queue, it's like a black box. It just sort of goes in, and there's some magic that goes on inside. We don't know what's happening inside. All we know is that when we ask for something from the top, we get the highest priority thing that's in there based on something we all agree ahead of time that's we're going to measure on, like somebody's temperature in line, or the priority, the urgency on a particular job task on a queue somewhere. And so we kind of want it to bubble up to the top in a really efficient way. And the idea with priority queues is we're dealing with live streaming data. Stuff's flying at us all the time, and we don't have time to maybe deal with the whole pile of it. So we really literally never get a chance to look at the whole pile of data. We just want the most important stuff to show up. So when we're ready to process the next urgent patient, we can just grab that one off the top. So that's a pretty cool idea, how we actually do that without sorting this constantly every time we get a new thing is the fun trick of all this. Okay. So if I say, okay, I have a key and a value, sort of a small node that has 2 data members, this just helps me identify, things uniquely. So I'm going to put that B5 in there, and I'm going to prioritize these things based on their second value, right? So what we want to be able to do is when we pop it, have it pull off the highest value. Now you're going to see here we got 2 values that are equal. So we haven't really said which one should get priority. So there's no guarantee of which one we're going to get, but we should get the highest priority one no matter what when we ask for it. Okay. And so, it's just a matter of, what's the most efficient way to do that. It turns out that you can implement that essentially in constant time. So that amortized over, lots and lots and lots of pops, you don't spend any more time getting the most important thing, regardless of how big that gets. And that's a pretty amazing thing. So priority queues are really powerful. If you got to deal with a lot of stuff and you just need to get the most important thing, almost like a sort, but you're only getting a sort for whatever you ask for. It's like, give me the most important thing now. Give me the most important thing now, right? So if somebody keeps shoving things into the bottom, you'll still keep getting things in priority order off the top at that moment in time. So that's what we're going to really break down next time. And the really nice thing about it is, you could have multiple threads, for those of you who know about multi-threading, pushing things in the bottom while some other thread is pulling things out of the top, right? So this is a really cool algorithm for dealing with stuff like that, like internet, demands for traffic, right? Demand for response on an internet server. Okay. So which one do we deal with first, kind of thing? Okay. So priority queues are pretty ubiquitous. Okay. Now the difference between a min and a max is pretty obvious. It's just going to depend on whether you want the lowest priority or the highest priority. And we'll talk about how we change the algorithm next week to do that. But as you can guess, it's pretty trivial. Like when we were sorting, you just kind of flip something around the other way and things should work out pretty good. But we'll talk about that next week too. Okay. So that's our min priority queue. Okay. So it's an abstract data type. It's for dealing with things that we can compare based on some key value. So we have to be able to, obviously compare stuff. And we'll see it implemented with something called a heap, which is a very cool data structure. Okay. So we'll look at that, but there are other ways to actually implement it too. There's something called a Fibonacci heap. There's a binomial heap. There's a variety of things we can actually use to implement it. Okay. And some of them are pretty darn cool. Okay. So we're NQing and DQing, and that's pretty much, it. So we'll look at the guts of that next week, I think. Okay. And the applications are pretty much everywhere, right? There's something called Dijkstra's shortest path algorithm that many of you have probably heard about and are probably curious about. And there's a derivative of that called the A-star algorithm, which is used in a lot of video games and a lot of other pathfinding algorithms. So we'll get to that eventually. But one of the key components of that is being able to throw things in this black bag and say, just keep giving me the longest or shortest thing every time I ask for it. Okay. And so we'll see some of that on homework 3. And we'll try to implement something like this in homework 3, but we'll probably not use the full binary heap. So we'll talk about that a little bit more down the road. But there's a whole sort of applications of this priority queue application. It's sort of underneath many, many, many different algorithms. Okay. So these are all the different ways we can implement it. Next time, we'll look at the binary heap implementation, which is really cool. I like it quite a bit. It kind of, I ignored it actually for many years. I thought, that thing isn't so interesting. Now that I understand it, I'm like, ooh, I can think of all sorts of really cool things I can do with that binary heap. So I think it's really worth actually looking into. Okay. Now, Lab 8, again, is optional. It's just one more exercising of our stack array class from last time. So I'll kind of leave you with this, but the algorithm is, if you want to call it that, if I only have stacks and I want to simulate a queue, right, using stacks. So if I wanted to create a class called queue via stacks, that was based on the stack array we made last time. So now we have two data structures working together. This is what I would do. I would NQ, NQ, NQ. And when it's time to DQ, I have to unpack. So I have to unpack into a temporary stack, right, until I'm empty. Okay. And then I can, DQ that last thing, and then I have to put the temporary stack back. Super inefficient. So it's really more about just kind of improving your ability to read the code and work with those structures in main. Okay. So if you want to tackle that, you can. Otherwise, I'd say just kind of try to get your homework knocked out and you should be in good shape. And that is all we have. Any questions on anything before we wrap it up? Okay. All right. Thanks, everybody. Have a great weekend. I will see you.